Okay, students, welcome back. Let's cover section 1.5. Okay, so section 1.5 is on some simple population models. I guess it's simple in comparatively simple. Whenever you're dealing with differential equations, nothing is simple. But these are about as simplistic as one can get, I suppose. Okay. Yeah. So the population model that you're probably very familiar with is actually called something called the Malthusian population model. And that's my exponential growth or exponential decay. Usually populations grow, some decay based on if there's a virus or a plague or something going through the population. Okay, so Malthusian population model. Okay, so we have dp dt is equal to kp. Okay, that's my differential equation. Okay, and we're going to say that we have an initial condition of p at time 0 is equal to what we call p naught, for p sub 0. Okay. Okay, so this is a separable differential equation. We're going to multiply both sides by dt. Oops, sorry about that. Okay, we're going to multiply both sides by dt, and I'm going to divide by that p. This gives me dp over p is equal to k dt. Okay, this is going to be, sorry, k dt. Okay, integrate both sides. This is going to be natural log of the absolute value p is equal to kt plus c. Okay, we're going to do e to both sides. We'll call that c1, and we'll get a absolute value p is equal to c2. Well, may not skip steps here. E to the kt times e to the c1, and we'll say that let e to the c1 equal to c2. Okay, so absolute value p, capital P, is equal to c2 times e to the kt. Okay, and so I'm just going to let c be c2. Okay, I'm just going to let c be equal to positive c2 if c is, maybe we can write that out. We'll just let c equal positive c2 if p is greater than 0, and negative c2 if p is less than 0. Then I can just use c as my constant. P is equal to c e to the kt. Okay, and so and we're going to say that at t equaling 0, p is equal to p naught. So p sub 0, p evaluated at 0 is equal to c e to the k times 0. Okay, well, this whole thing goes to 1. So C is equal to P sub 0, which is P naught. So that's kind of why we define it that way. So C is equal to P naught. So P is equal to P naught E to the KT. Okay, and that's kind of the population model that you've grown up with. Okay, if K is greater than 0, then we have population growth. If K is less than 0, if K is negative, then we have population decay. Okay, let's do a problem based on this. The number of bacteria in a certain culture, that's a bacteria culture, not a group of people. Okay, certain culture grows at a rate that is proportional to the number present, or basically to the population size. Now, if the number increased if the number of bacteria increased from 500 to 2,000 in 2 hours, find the time it takes for the bacteria to double in size. For the bacteria to double in size. Okay. We have P is equal to P naught E to the KT. We figured that out from the differential equation, which was dP dt equals K P, right? dP dt is equal to Kp. Was it? Okay, and we found that to be the solution. This is the general solution to that differential equation. Okay, we don't know what P naught is, and we don't know what K is. Okay, so those are things that we might need to figure out. Okay, so we can let P naught be equal to 500 because we could start the clock there. We could have a little stopwatch and okay, start the clock at when we're at 500. We don't have to start the clock when we only have 2 bacteria. Okay, we can start the clock when we have 500 bacteria. Okay, so we're going to start the clock there. Okay, let P naught be equal to 500. Okay, and so let's solve for K. Let's figure what K has to be. Okay, so P is equal to 500 e to the KT. And we're going to say that after 2 hours, I should have 2,000 bacteria in the culture. So 2,000 is equal to 500 e to the 2k. Okay, let's divide by 500. We get 4 is equal to e to the 2k. Okay, then we get let's take the natural log of both sides. Natural log of 4 is equal to the natural log of e to the 2k. That cancels. So natural log of 4 is equal to 2k, divide by 2, and we get k to be equal to the natural log of 4 over 2. So we can simplify that a little bit more by using the properties of natural logs. This is 1/2 natural log of 4, okay, which is 4 to the 1/2 power, which is just the natural log of 2. So there's k. Okay, so the natural log of 2 is equal to k. That's helpful. Because once again, what do we have? We have p equals 500 e to the kt. Well, now we know what k is. Okay, so our function really becomes p equals 500 okay, e to the k, which is natural log 2 times t. We want to know what's our doubling time. What happens to be our doubling time here? Okay. And so what I'm going to do is say, well, our doubling time would be when this 500 equals 1,000. So I'm going to say, let's solve for time when we have 1,000 is equal to 500. 1,000 is our final result, but we start with 500. Well, now how long is it going to take for it to double? We have e to the t times natural log of 2. Okay. We can take that in t and make it an exponent. So this is, and divide by this 500. And we get 2 is equal to e to the natural log of 2 to the t. The e and the natural log are going to cancel. I'm left with 2 is equal to 2 to the t. So what is t? Well, t is equal to 1, because that would have to be the exponent there. And so that's 1 hour. So it will double every hour. Okay, so it will double every hour. So it doubles every hour. Okay, so find the size, or find the time for the bacteria to double in size. Now, does that make sense that it would double every hour? Well, if I take my initial 2,000, okay, going from 500 to 2,000, well, how many times is it doubling? Well, it would double from 500 to 1,000, and then it would double from 1,000 to 2,000. So this would take an hour, and this would take an hour. Okay. And does that make sense? Does that make sense that the time was 2 hours? Yes, it does, because that's exactly what's in my problem, is that we have e to the k, which was k was natural log of 2, times 2, right? So, this did increase when t was equal to 2. We could prove that this is going to be 2 to the second power, which is 4, and 4 times 500 is 2,000. So it does double every hour. Okay, we could kind of generalize this. If we didn't know what P or P naught was, it really doesn't matter. We could go back to our original equation here. Okay, and say, well, what would happen if we do double? Okay, is there a general rule for doubling? There actually is. If we go P equals P naught e to the KT, and I just let P equal 2 P naught, then I can divide by P naught, and I get 2 is equal to e to the KT. Take the natural log of both sides, and I get the natural log of 2 is equal to KT. And so if you can figure out what K is, okay, if you can figure out what your exponential growth rate is, then your time is just equal to the natural log over K, natural log of 2 over K. That's kind of a nice little result there as well. Okay, is that we really didn't need to know what P naught was or P in order to get the doubling time. We just need to know what K is. Now we needed to know specific values for this specific particular problem, so we could have a particular solution. But again, you know, we only need to solve for K. And once we have K, we can find the doubling time. So that's kind of cool. Okay. We can also find something called half-life as well, if it's decaying. Okay, just based on the K value. Okay, the K constant, the growth or decay rate. I should say exponential growth or decay rate. Okay, let's move on to the logistic population model. So the logistic population model. Okay, and the logistic curve is an interesting curve. It looks like this. It starts out exponential, and then halfway up, it bends and it hits a limit. Okay, and this limit is called the carrying capacity to the system. Okay, I used to call this the Thanos model, after Thanos had like snapped half of the people from the universe, and I really said that Thanos was not very smart because he didn't understand the logistic population model, in that if you snap half the people, you're going to hit that carrying capacity again. Okay, you need to like snap like 3/4 of the people from the planet, all the planets in the universe, and then you'll be, you know, like down here, and then you'll have room to grow again. But if you snap only half, you're going to hit that carrying capacity again, you know, relatively quickly, because you've got exponential growth until halfway, and then you start killing off more and more people because there's too many people. Okay, or too many rats in a cage, or however, you know, too many cultures on or bacteria on a culture, or, you know, culture disk, or however you want to think about it. But, you know, there ends up being not enough resources to carry a certain number of individuals, and so, you know, you can't have a million rats in a cage. So it just, you know, unless you have a really, really big cage, I guess. Okay, so again, this is kind of the Thanos model. Okay, so let's analyze this. Let B of t, okay, let B of t equal birth rate. And D of t equal death rate. P dt equals B of t minus D of t P. So it's birth rate minus death rate, and then it depends on, you know, where we're at. in the population, okay, if birth rate remains constant, and death rate is proportional, to the instantaneous population, then we rewrite the equation as dp dt equals b sub 0 minus d sub 0 p times p, where p, the population times 0 is equal to p naught. Okay. Okay, I'm going to factor out a b naught. Okay, so dp dt is equal to b naught times 1 minus d naught over b naught p times p. Okay, and we're going to let, I just want to put it in a certain form, let r equal b naught, so that'll be birth rate at time 0, and c equal b naught over d naught, which is initial birth rate, over initial death rate. And so I can rewrite this as dp dt is equal to r, okay, times 1 minus, and this is the reciprocal of b naught, so this is going to be p over c times p, okay? Notice that d naught over b naught, the reciprocal of that, or 1 over c, is d naught over b naught. So that's why the c is in the bottom there. Okay, this is called the logistic equation. And C is called the carrying capacity. That's why it's C. Of the population. The max that the population can hit before decaying, before starting to decay. It just, you know, you're at that point, your death rate is exceeding your birth rate. Okay, the carrying capacity of the population. And the highest population and the highest population, the environment can sustain. Okay, that's B naught over D naught. Means that ratio of birth to death. Okay, so let's think about solving this differential equation and how we might go about it. Okay, we're going to let P naught, or P sub 0, or P at evaluated at 0 equal P naught. Okay, and dp dt equal my new differential equation. I should really write this as a parenthesis, probably 2 parentheses. Okay, dp dt is equal to r times 1 minus p over c times p. Okay. Okay, so let's try to separate this. Notice that C is a constant. Okay, and so is R. Okay, R and C are constants, so we're going to treat them as constants. Okay. So let's try to do some separable differential equations here. Okay, so dp dt, if I were to divide, let's just say that we divide by this guy, 1 minus p over c times p. Okay, we'll have the dt go over here. Okay, and divide by 1 minus p over c times p. Okay, so we're going to get dp over 1 minus p over c times p is equal to r dt. Okay, after I separate, okay, I get this guy here. Okay, so now what I want to do, okay, is I want to multiply both top and bottom here by c. So let's multiply both top and bottom by c. Okay, so I don't have to deal with some weird fractions here. So this is CDP. Okay, CDP over C minus P times P is equal to R dt. Okay. So this really is, I'm going to move the, because now what I want to do is some partial fraction decomposition. Okay, I'm going to say that C over C minus P times P is equal to A over, I'll just use capital letters, A over C minus P plus B over P. Okay, so let's do some partial fractions on this. Okay, if I multiply through by C minus P over times P, and then distribute that, I get C is equal to A times C minus P times P. No, A times P. The C minus P's are going to cancel out. This will be, I'll just not skip steps. So C minus P times P plus B times C minus P, P over P. Okay, so these guys cancel there, and those guys cancel there. With C is equal to A, P plus B times C minus P. Okay, okay, distribute. Okay, and we get AP plus BC minus BP is equal to C. Okay. Okay. And so I'm going to rewrite this. I'm going to say that I'm going to add a 0p plus c. Okay, because my variable is p here. Don't forget that that's the variable dp dt. Okay, the variable p. This is a constant function. This is going to be ap minus bp plus bc. If I go 0p plus c is equal to, factor out the p, I'm going to go like this, a minus b, and then I'm going to factor out the p here, plus bc, then we could say that a minus b is equal to 0. and b is equal to 1, because there's just an imaginary 1 in front of there. So b is equal to 1. And so if a minus b has to be 0 and b is equal to 1, then a has to be 1. Okay, so how does that help me out here? Well, that tells me that c over c minus p times p is equal to 1 over c minus p plus 1 over p. Okay, so I can take this guy and rewrite him in a different form. Okay, so we're going to take that guy, c over c minus p times p, okay, dp equals r dt, and then we're going to rewrite it as 1 over c minus p, and this just helps me integrate. Okay, I'm just setting up the integration to help me integrate, make my life a little simpler in integrating this. Okay, c minus p plus 1 over p, okay, dp, okay, is equal to r dt. Let's integrate both sides now. Okay, this is just going to be, we could do a u sub on this. Okay, again, what's the variable? It's p. So u is equal to c minus p du is equal to -1 dp. Okay, so if I do use a natural log on this, 1 over u, just keep in mind we have an extra negative there that we have to deal with. Okay, so well, I'll continue this. This is 1 over u. Okay, and then if we multiply both sides by a negative, then this becomes negative du. Okay, integrate that. I'll separate these into two separate integrals. Okay, so this is negative natural log u. Okay, but what was u? It was c minus p. So this is negative natural log of c minus p. Okay, and then plus, what's the integral of 1 over p? So the integral of 1 over p is just natural log of p. Okay, I could have a plus c here, but I'm going to toss that to the other side eventually. Okay, and so what happens here? Well, this is the natural log of p minus the natural log of c minus p. And from our properties of natural logs, this is just going to, the difference of two logs is the quotient of the values. So natural log of p over c minus p. Oh, okay. There's absolute value there as well. Okay. Is equal to, now what's the integral on the other side? The integral on the other side, that's just RT plus C. Okay, maybe we'll call that a C1. Okay, is equal to RT plus C1. Okay, so the natural log of P, so let's make this base E. Okay, get rid of those. Natural log of P over C minus P is equal to C2 e to the RT. Okay, and then I'm going to do my little trick with the absolute value, basically turning C2 into C. Okay, I can get rid of the absolute value because it doesn't matter what C was, it could be negative or positive. Okay, so P over C minus P is equal to C. Actually, do I want it to be C? Let's just let it be C3. Because I don't want to confuse this C, which is the carrying capacity, with that C3. Okay, so e to the RT. Okay. Okay, so now I'm going to multiply both sides by C minus P. Okay, and I get P is equal to, let's distribute C times C3. The C3 is a constant. Okay, it's just what I got from my integration. It's an integration constant. C is my carrying capacity. Okay, remember that's B naught over D naught. Okay, so those are two different C's. This is the C3 is just a constant of integration. Okay, and then that's e to the RT minus C3P. We'll do PC3. P3 e to the RT. Okay. Okay, and the goal here is to get P by itself. Okay, so I'm going to toss this guy to the other side, and I'm going to say that that's P plus PC3 e to the RT is equal to C C3 e to the RT. Okay, good. Okay, and then I'm going to factor out P, that's 1 plus C3 e to the RT is equal to C3 e to the RT. Okay, and then divide by 1 plus C3 e to the RT, 1 plus C3 e to the RT, okay. Cancel out, I get P equals okay, C3 e to the RT over 1 plus C3 e to the RT. Okay, so now what would happen if I divided both top and bottom by C3, or sorry, by e to the RT? So let's divide both top and bottom by e to the RT. Okay, and what I would get is I would get CC3 over e to the negative RT, because this would be what end up with being 1 over e to the RT. And so that would be 1 over a positive exponent would make it negative, plus C3. Okay. Okay, so now let's let, okay, P sub 0 equal P naught. Okay, at time 0, we're going to get P naught. So we're going to figure out, okay, what does P naught have to be then? Okay, and so if we plug in 0 for T, P naught would equal CC3 over e to the negative R times 0 plus C3, which would be e to the 0, which is 1. So this is C3 over 1 plus C3. Okay, so that's P naught. Okay, so let's solve this for C3. I don't like that C3. If we could get rid of the C3 and put it in terms of P naught and C, that would be awesome. Okay, so P naught is equal to C3 over 1 plus C3. Let's multiply 1 plus C3. And we get 1 plus C3, P naught is equal to C3. Okay, good. Okay, distribute the P, we get P naught plus C3 P naught is equal to CC3. Okay, good. I like where this is going. Okay, let's toss this guy over here. and we get C3 minus C3 P naught is equal to P naught. Factor out the C3, we get C minus P naught equal to P naught. So P naught over C minus P naught is equal to C3. So C3 is equal to P naught over C minus P naught. Okay, so let's replace that back into this equation that we got. Okay, let's see what we can do with that. So we'll say that P is equal to C times P naught over C minus P naught. Okay, over e to the negative RT plus C3, which is P naught over C minus P naught. And let's see if we can clean up some of these fractions here. Okay. Let's bring the C minus P naught down. Okay, and so P is equal to C P naught over e to the negative RT plus P naught over C minus P naught times C minus P naught. Okay, and what that's going to do is it's going to clear the fraction there after I distribute. Okay, so P is equal to C P naught, okay, over C minus P naught e to the negative RT plus P naught. Okay, and I'm going to rewrite this. P is equal to C P naught over P naught plus C minus P naught e to the negative RT. Okay, where P naught is the initial population. Okay, and C is equal to B naught over D naught, which is the initial birth rate. Over the initial death rate. So it's all based on my initials. Okay, my initial values. And so I'll just put a little t here because this is the population at time t. And what is C? C is the carrying capacity. Okay, so we can see that if we take a limit as t goes to infinity, okay, then this thing goes to 0. Okay, e to the negative RT, that's going to go to 0 as t goes to infinity. So that's going to push this term to 0. Okay, and then I would just get C times P naught over P naught. Those two would cancel, and I would go to C. Okay, then I'll say, then C minus P naught e to the negative RT goes to 0. And so P equals C. Okay, P goes to C. Let's put arrow. Okay, so yeah. Oops. So pretty cool value there. Okay, pretty cool model. And once again, we're going to start at a initial population value, P naught. We're going to get a birth rate and a death rate. And then this is our C, which is our carrying capacity. And they all kind of have the same behavior. Different values are going to create different families of graphs, families of curves. They're all going to have the initial value. They'll hit their half of their total population. Okay, half of the carrying capacity. This is C over 2. Okay, they hit half of the carrying capacity, and then they start dwindling their populations the closer and closer they get to C. Okay, so this is the logistic population model. Okay, so you may have used this in a class before, but now you know how it was derived. Oops. And it's just a basic separable differential equation. Okay, and very powerful differential equation. Okay, pretty cool. Pretty cool. Okay, let's do an example, a quick example of this before we finish out this section. Okay, if P naught is 20, okay, and P at time 10, population at time 10 is 50.87, and the population at time 15 is equal to 76.68, then find the population at time 30. Okay, what's the population for the logistic model? Okay. So we need to set up two equations actually, because we have two different scenarios here. Okay, so the population at time 10 is going to be equal to C times P naught, which is 20, over 20 plus C minus 20. Okay, and then that's E to the negative R times 10. I'll clean that up in a minute. Okay, we also have, oh, that's a P10, sorry. P10, we also have P at time 15 is equal to C times P naught, which is 20, all over 20 plus C minus 20, E to the negative R times 15. Okay. So this is equal to, well, what's P10 equal to? P10 is equal to the 50.87 is equal to, this is 20C over 20 plus C minus 20 E to the negative 10R. Okay. And then over here we have 76.68. Okay. Is equal to 20C. Okay, over 20 plus C minus 20 E to the negative 15R. And I'm not going to go through, we have a system of equations with two equations and two unknowns. Okay, and so the working out of the system is actually very complex, and you can do it actually more efficiently via computer. So if you plug in this system of equations, okay, you will find that C is equal to 500.37 if you solve that via computer, and R is approximately 0.1. Okay, so the growth rate is roughly 10%, and the birth rate over death rate is roughly 500. Okay, initial birth rate to initial death rate is roughly 500. So we get C and R1. Okay, so that tells me that P of t is equal to 20 times 500.37 over 20 plus 500.37 minus 20 e to the RT. R is 0.1. Okay, 0.1 times t, or basically t over 10. Okay, so e to the t over 10. Okay, so now I could clean this up a little bit if I wanted to. This would be 20 times 37, or 500.37. Let's go to my calculator here. I don't know if it's going to come up or not. Oh, it does come up. Okay, good. Okay, and so clear that. We get 20 times 500.37. Okay, is 10,007.4. Okay, so P of t is equal to 10,007.4 over 20 plus 500 minus 480.37 e to the t over 10. Okay, so let me clean that up a little bit better. Okay, so that's my function, P of t. We want to know, well, what's P of 30? Okay, P of 30, we just plug in 30 here, and we get 10,007.4 over 20 plus 480.37 e to the 30 over 10, which is 3. So I can rewrite that as 3. Okay, just plug in 30 over 10 is 3, and then plug that into a calculator. Okay, and let's see what we get. Okay, so we've got that on top divided by 20 plus 480.37 times, oops, yeah, times e to the 3. Oops. To the 3, let's see what happens here. Oh, it should be -3. I'm sorry. Why? R is 0.1. Okay, I think we did this. Let's go back and see why this is. This should be R is 0.1, and it's a negative. It's a negative R. That's right. Okay, so it's negative. Okay, so that should be a negative. Okay, that's fine. And then that's a negative. Okay, so let's go back and put in, make sure that that's a negative. Sorry about that. So and then put in the negative 3. Whoops. Not too quick. There we go. Let's see. Oh, I put in the answer. Oh gosh, this is. Okay, let's just do this. 10,000 keeps pulling the answer in the previous. Okay, 10,000.7, 10,007.4 divided by, let's grab that. Let's get rid of the answer portion. Let's see what happens. There we go, finally. Okay, 227.87. Okay, is the population after 30. Okay, so we know that the population couldn't have been 1, because at 10 it was 50, and at 15 it was 76.68. So this makes a little bit more sense, right? Because again, at the very beginning, at 10 it was 50, at 15 it was 76, so it's still going up, and it would continue to go up even if it was hitting a carrying capacity. It would continue to go up, and so we need a value that's bigger than that. So yeah, the negative works, and so it's 227.87. Okay, so roughly 228 whatevers in the population. Okay, after time 30. Okay, I will see you guys in the next video.